Hello, dear students. Welcome to the lecture 13 of Artificial Intelligence and Machine Learning. And today's topic is probability as part 1. Okay, so let's start. And
Basic probability theory, terminology. An experiment has a set of potential outcomes, e.g., throw a dice, look at another sentence.
okay, one moment. Okay, so let's continue.
The sample space of an experiment is the set of all possible outcomes, e.g., 1, 2, 3, 4, 5, 6.
Okay, so the sample space is the possible set of all outcomes. Okay, so in the dice example, there are 6 possible outcomes. So the sample space is 1, 2, 3, 4, 5, 6.
For machine learning, the sample spaces can vary large.
It is so true. For example, there is the newest deep learning algorithm trained on millions of documents. Let me find it. What was its name? I can't remember its name, but I will see it. Let's check it out. No, not this. Okay, let me search differently. Machine learning project. Type sentence, get article. I think it may be OpenAI. Let me check it. Yeah, GPT. Okay, it is GPT-3, I believe. Okay, latest GPT project. Yeah, GPT-3. Okay, so let's get read it.
Generative Pre-trained Transformer 3 (GPT-3) is an autoregressive language model that uses deep learning to produce human-like text. It is the third-generation language prediction model in the GPT-N series and the successor to GPT-2, created by OpenAI, a San Francisco-based artificial intelligence research laboratory. 2. GPT-3's full version has a capacity of 175 billion machine learning parameters. GPT-3, which was introduced in May 2020 and is in beta testing as of July 2023, is part of a trend in natural language processing (NLP) systems of pre-trained language representations. 1. Before the release of GPT-3, the largest language model was Microsoft's Turing NLG, introduced in February 2020, with a capacity of 17 billion parameters or less than 10% compared to GPT-3. 4.
Okay. Okay, all right. So you see, it has 175 billion parameters. Can you imagine how much RAM memory would just a single letter take when there are 175 billion and it is machine learning parameters? So I think by this they refer how many features are used probably. Okay, let's continue reading.
The quality of the text generated by GPT-3 is so high that it is difficult to distinguish from that written by a human, which has both benefits and risks. 431 OpenAI researchers and engineers presented the original May 28, 2020 paper introducing GPT-3. In their paper, they warned of GPT-3's potential dangers and called for research to mitigate risk. 34 David Chalmers, an Australian philosopher, described GPT-3 as one of the most interesting and important AI systems ever produced. 5.
Okay, and okay, let's continue to our course. So you see, it can be very large, and let's continue. Okay.
An event is a subset of the sample space.
Okay, so we have sample space and then we have events which are subset of the sample space. So if when we roll a dice, our sample space is like this. An event can be dice getting as 2 or getting 3 or 6 or getting even numbers such as 2, 4, 6 or odd numbers 1, 3, 5. Each of them can be called as a different event. Okay, machine learning.
A particular feature has a particular values. An example, i.e. a particular setting of features values.
Okay, for example, label chicken. Okay, so let's continue. So events, we are interested in probabilities of events. So you see they are called as they are called with prefix p, probability, and probability of dice getting 2, probability of getting labeled survived, or probability of getting labeled chicken. So these are from for example text, and this is from dice rolling, and probability of parasitic gap, and this is something else, so let's read it as well.
Parasitic gap. In generative grammar, a parasitic gap is a construction in which one gap appears to be dependent on another gap, that is, the one gap can appear only by virtue of the appearance of the other gap, hence the former is said to be parasitic on the latter, e.g. which explanation did you reject __1 without first really considering __2? While parasitic gaps are present in English and some related Germanic languages, e.g. Swedish, see Engdahl 1983, their appearance is much more restricted in other, closely related languages, e.g. German and the Romance languages. 1. Japanese linguistic scholar Fumikazu Nionuma has attempted to differentiate between parasitic gaps and coordination in his research, as he believes the two are often confused. 2. An aspect of parasitic gaps that makes them particularly mysterious is the fact they usually appear inside islands to extraction. Although the study of parasitic gaps began in the late 1970s, no consensus has yet been reached about the best analysis.
Okay, so the following sentences illustrate typical parasitic gaps, and the parasitic gaps are marked with p subscript. Okay, so you reviewed that book without actually reading it. No gap at all present. In this case, there is no gap. What book did you review without actually reading? Okay, here parasitic gap is possible, such as let's see if they given the example. Let's find some better example. So parasitic gap is a grammar thing. It is not related to our lecture right now, but okay, so okay, anyway, I will pass it. If you are interested in, you can look it. So this is something that is, let's say, linguistic, and the probability of parasitic gap existing in a sentence, for example, or probability of meat word appearing in the text, such as, okay, and random variables.
A random variable is a mapping from the sample space to a number, think events. It represents all the possible values of something we want to measure in an experiment. For example, random variable, x, could be the number of heads for a coin.
Okay, number of heads for a coin can be the random variable x. So if it is the case, let's see the space. Okay, so let's think that we are 3 times throwing a coin, flipping a coin, and it can be either head or tail, as you know. So the head count, that when we do it 3 times, it can be 3 times head, or it can be head, tail. Okay, coin flip. Oh, tail. Okay, not tail, tail. Or tail. It can be head, tail, head. It can be head, tail, tail. It can be tail, head, head. It can be tail, head, tail. It can be tail, tail, head, and it can be tail, tail, tail. So if our random variable x is the number of heads for a coin, in this case the x is 3, in this case the x is 2, in this case the x is 2, in this case the x is 1, in this case the x is 2, 1, 1, 0.
Really, for notational convenience, since the event space can sometimes be irregular.
Okay.
We're interested in probability of the different values of a random variable. The definition of probabilities over all of the possible values of a random variable defines a probability distribution.
Okay, so this is what defines probability distribution. So the probability of x being 3 is 1 over 8. Why? Because it exists only one time in the 8 different events. Okay, so you see each one of these are the events, and all of them composes our event space. Okay, and it was called sample space. Okay, and when we flip coin 3 times, our entire sample space is this, which are head, tail, head, tail, tail, head, tail, tail, head, and tail, tail. Out of this sample space, the probability of x being 3 is 1 over 8, because we have 8 events and only one of them has number x as 3, the event x as 3. So the probability of x being 2 is 3, because in 3 events it is 2. The probability of x being 1 is 3, because in 3 events it has 1. By the way, 3 over 8, 3 over 8, and 1 over 8, and the probability of x being 0 is 1 over 8. So when we sum all of the probabilities, you see we get 1. Okay, this is always a rule. When we sum all of the event probabilities, it is always equals to 1.
Probability distribution. To be explicit, a probability distribution assigns probability values to all possible values of a random variable. These values must be greater than equals 0 and less than equals 1. These values must sum to 1 for all possible values of the random variable.
Okay, so in this case, this is wrong, because some of them is not equal to 1, or here, this is wrong, because some of them is not equal to 1 as well.
Unconditional, prior probability. Simplest form of probability is Px.
Okay, so unconditional and prior probability, unconditional and prior are meaning same. Okay.
Prior probability, without any additional information, what is the probability? What is the probability of a heads? What is the probability of surviving the Titanic? What is the probability of a wine review containing the word banana? What is the probability of a passenger on the Titanic being under 21 years old?
And so, okay, one moment. Okay.
Joint distribution. We can also talk about probability distributions over multiple dependent variables.
Okay, it is different when they are dependent. Therefore, there are two cases. One of them is pure or unconditional probability, and the second one is joint distribution. So it is called, displayed as PXI, probability of X and I. Okay, a distribution over the cross product of possible values. So this is joint distribution. So the probability of your passing machine learning true is 0.89 probability of machine learning pass, and probability of not passing it is 0.11, and then we have in English pass. So probability of English pass is true for 0.92 and false for 0.08. So there are joint probabilities of passing both of them. Passing both of them has 0.88. Passing machine learning and failing English is 0.01, and passing failing machine learning and passing English is 0.04, and failing both of them is 0.07. So this is dependent variables joint distribution. Therefore, it is not like that we are multiplying these two. Okay, so if we multiply them, you see we get 0.82. However, they are 0.88 because they are dependent probabilities. Okay.
Still a probability distribution. All values between 0 and 1, inclusive. All values sum to 1.
This is important. All values sum to 1.
All questions probabilities of the two variables can be calculated from the joint distribution.
Okay, from this joint distribution, we can calculate the probability of passing English alone. Okay, so this is joint distribution table, and from here we can calculate probability of passing English. How can we do that? How can we do it? It is simple actually. We can do it by in which rows the English pass is true. It is true here and it is true here. So when we sum them, we get 0.92. As you can see, sum this row because the English pass here is true, and sum this row because English pass is true. Okay, when we sum them, it is 0.92. So it is displayed as like this. All right, and then
Conditional probability.
okay, these were one moment. All right. Okay, so this is how we calculate probabilities. So when you type like this, it is multiple dependent variables, probability distributions, probability of X and I. Okay, so this is AND, as you can see. And here, then we see conditional probability.
As we learn more information, we can update our probability distribution. PXY models this read probability of X given Y.
When Y is given, we can see the probability of X. Okay, so this is conditional probability. This is different than the previous one.
What is the probability of a heads given that both sides of the coin are heads?
You see, when both sides of coin are heads, the probability of heads is 100. 1.
What is the probability the document is about chicken, given that it contains the word meat?
So when it contains meat, the probability of chicken is higher than a document that doesn't have a meat word.
What is the probability of the word fish, given that the sentence also contains the word meat? Notice that it is still a distribution over the values of x.
Okay, so the conditional probability is something like this.
In terms of prior and joint distributions, what is the conditional probability distribution?
Okay, so there are prior and joint distributions and conditional probability distribution. Okay,
Given that y has happened, in what proportion of those events does x also happen?
so we know that y has happened, therefore the probability of x happening is their crossing section here, not here. We know that it can't be here, but we know that it can be here or it can be here. Okay.
What is PML pass equals true, eng pass equals false?
Okay, so we know that it has failed English, so it can be either this one or this one. Therefore, the passing of machine learning is 0.1 over 0.1 plus 0.07. Therefore, it is 1 over 7 basically. Let's see it. So probability true and false here you see 0.0.01 and our sample space in this case is being, since we take only false as English, 0.01 plus 0.07, therefore it is 1 over 8 as I said, so the probability is 0.125 for this case. So this is what is conditional probability.
Notice this is very different than PML pass equals true equals 0.89.
Okay.
Both are distributions over x.
Okay, so there is unconditional prior probability Px and there is conditional probability Pxi. Okay, so it differentiates when you use comma or this letter. Okay. All right, so you see these are the probabilities.
A note about notation. When talking about a particular assignment, you should technically write Px equals x, etc. However, when it's clear, we'll often shorten it. Also, we may also say Px or Px to generically mean any particular value, i.e. Px equals x.
So P true false is like this. Okay, we have seen that. And then properties of probabilities. So P, A or B. What is A or B? What can be? Okay, so P, A or B equals to PA plus PB subtracting PA and B. So therefore it is this area. Here, follow my mouse cursor. Here and here. Okay. So we subtract their crossing section here from the entire space. And this is another notation. If it is like this is 1 minus probability of E, more generally.
Given events E equals E1, E2, N.
So it can be written like this. Okay, there is chain rule as known as product rule. So Px over I is written like this, or it can be written like this as well.
we can view calculating the probability of X and Y occurring as two steps. 1. Y occurs with some probability p, Y. 2. Then, X occurs, given that Y has occurred.
Okay. So the chain rule is something like this. P and let me read it.
P x y z equals P x y z P y z.
Or it can be written like this.
P x y z equals P x y z P z.
Or it can be like this.
P x y z equals P x y z P y z P z. P x y z equals P y z x P x.
Okay.
Applications of the chain rule. We saw that we could calculate the individual prior probabilities using the joint distribution. What if we don't have the joint distribution, but do have conditional probability information? This is called summing over, or marginalizing out, a variable.
Okay, so
Bayes' rule, theorem.
there is Bayes' rule.
Allows us to talk about p, y, x rather than p, x, y. Sometimes this can be more intuitive. P, disease, symptoms. For everyone who had those symptoms, how many had the disease? P, symptoms, disease. For everyone that had the disease, how many had this symptom?
You see, the right side means that it has happened, and therefore the probability of the left side. This is what it means. And they are explain it like this in this case.
P, label, features. For all examples that had those features, how many had that label? P, features, label. For all the examples with that label, how many had this feature? P, cause, effect versus P, effect, cause.
Okay, and then gaps.
I just won't put these away.
Okay, so there is direct object and
These, I just won't put away.
this is gap.
I just won't put away.
And
What did you put away? The socks that I put away.
okay, and this is parasitic gaps. Okay, cannot exist by themselves. These I will put away without folding. Okay, and these I will put my pants away without folding. And these I will put away without folding them. So we can read more about parasitic gaps here.
Doug's parasitic gap. Doug, I said one morning, you still have to put away this laundry. He said okay and started with the socks and underwear, since you don't have to worry about them getting unfolded when you stuff them into a drawer. He kept out one pair of socks, saying, "These, I just won't put away because I'm gonna wear." A sensible choice. Of course, I have to watch out for that slippery slope. Next, he might leave out a pair of pajamas because he's going to wear them tonight. And then a pair of jeans because he's going to wear them tomorrow. Before you know it, the piles of folded laundry will become a clothes smorgasbord that lasts the whole week, like the one on the couch in Mom and Dad's house when I was growing up. Anyway, while Doug put away the rest of his laundry, I had to write down what he said in my memo book, a topicalization with a parasitic gap in a finite clause. Topicalization is the name for putting at the front of a sentence some phrase that would ordinarily appear later. So instead of the more ordinary "I just won't put these away," we get these "I just won't put away." Onto the parasitic gap. In order to talk about parasitic gaps, I have to talk about ordinary gaps first. A gap is a place in a phrase where something is missing. So in these "I just won't put away," there is a gap between put and away, assuming that in an ordinary sentence, that's where the direct object would go, "I just won't put these away." You know something is missing, because you can't just say, "I just won't put away" all by itself, you need a word or phrase saying what isn't getting put away. Of course, direct objects can also appear after the away, as in "put away this laundry," but that's not important for this post. The piece that's missing from a gap usually shows up somewhere else in the sentence, where it is sometimes referred to as a filler. In Doug's example, these is the filler corresponding to the gap in "I just won't put ____ away." Gaps also appear in WH questions and relative clauses, where the WH word or the relative pronoun act as the fillers for the gaps.
Okay, so the topicalization, these "I just won't put away." VH question, what did you put away? Relative clause, that sucks that I put away. Okay, and okay, anyway, this is not that much important. Okay, now let's return to our topic.
Frequency of parasitic gaps. Parasitic gaps occur on average in 1/100,000 sentences.
Okay, 1 over 100,000 sentences, it happens. Problem.
Maggie Louise Gall, aka ML Gall, has developed a machine learning approach to identify parasitic gaps. If a sentence has a parasitic gap, it correctly identifies it 95% of the time. If it doesn't, it will incorrectly say it does with probability 0.005. Suppose we run it on a sentence and the algorithm says it is a parasitic gap. What is the probability it actually is?
Okay, let's just try to think about this question. So, if a sentence has a parasitic gap, so this is the condition, as you can see, if it has, it correctly identifies it 95% of the time. So this is the conditional probability. If it has 95% of the time, it is correct. However, if it doesn't, this is also another conditional probability. It will incorrectly say it does probability with 0.005. So let's make some math here. So parasitic gaps occur on average 1 in a 100,000. So if it has, it calculates 95% of the time. So if it is that one time in a 100,000 time, it is 0.5 times correct. However, there are still 999 cases, and out of these cases, it says it will incorrectly say it does with probability. Incorrectly say. Okay. So it will say correctly incorrectly say it does with probability. Okay. So in these many cases, it will say 0.5 probability. Incorrectly, how many cases that it makes? Let's calculate. Okay, 9999 and 0.05. Okay, it is like this. So this many times it will say false, and here we get this many. So we calculate it plus 0.05. Okay, so this many times out of 100 times it will say incorrectly. So when we split it to 1,000, 100,000, so the probability of actually saying incorrectly is actually being like this. However, I am not sure if we have calculated correctly. Suppose we run it on a sentence and the algorithm says it is a parasitic gap. What is the probability of it actually is? Okay, let's read it. Okay, G equal to gap and T is test positive. What question do we want to ask? I will rethink about that. Okay, let's make this as 1 million cases. If there were 1 million cases, there will be 10 cases of true. So if this occurs, if it is correct, it will know, or let's make it 10 million. It will say 95 times true and 5 times false. Out of use cases, 100 cases of 10 million. And if it doesn't have, which makes 9999 cases. Okay. So out of these many cases, okay, it will incorrectly know, it will incorrectly say it does. And it will correctly say it does have 99.5 times. Okay, usually this is some kind of harder question. So it will be correct for 99.5 cases. Okay, so P G over T. So if T happens, test positive, what is the probability of gap? Okay, let's see. So we can calculate it like this. If G happens, what is the probability of T? And multiply with probability of G and divide by P probability of T. So it becomes like this. Then we start calculating. Okay, here the probability of when G gap happens, we know it, okay, true like this, and we multiply it with the overall probability of gap. Okay, we did this here. This is what we have calculated. 1, and it makes like this. Then it is divided with okay, plus, okay, so we have also calculated it like this, and then it has another probability join. Where is this coming from? Oh, I think this is the answer, or okay, plus, okay, no, there is nothing like this. So let's calculate it. Okay, what is the result of this? Something like this. Okay, this is our first letter, and now then we have this, and then we will divide them. Okay, this is exactly as we have found here, you see, and then we divide them, divide this with this. Okay, so this is the actual probability. But then there is this one. Interesting. Okay, let's see if this exists on Google. Okay, so this has been asked maybe. Okay, this is the slides we are using. Okay, it is equal to something. Yes, this is also what we have found. So this is the probability, but this is incorrectly changed. Therefore, our calculation was correct. Interesting. When I make this PDF, it is displayed like this here. Why? This is so weird. But it is correct here. Okay, let's continue. I think it is clear now. Okay, probabilistic models.
Probabilistic models. Probabilistic modeling.
Okay, so the first part was all about getting the idea of probabilities. Now we are going to see in machine learning probabilistic models. Okay, it was like a preparation. So we have training data and we train it to generate a probabilistic model. Okay.
Model the data with a probabilistic model. Specifically, learn P features label. P features label tells us how likely these features in this example are.
Okay. And this is correctly displayed here, but when we turn it into PDF, it is incorrectly displayed. So to fix it, I will make a modification to this slide. Let's make it like something like this, and let's paste it over here. So we will be keeping both, and okay, let's continue.
An example, classifying fruit. Training data.
Okay, so as a training data, we have examples and label. So in the training data, we have the features of the examples, which are red, round, leaf, 3 O's weight, and labeled as apple. Green, round, no leaf, 4 O's apple. Yellow, curved, no leaf, 4 O's banana. Green, curved, no leaf, 5 O's banana. And then our probabilistic model will generate a model that will give us the probability of the prediction. Okay.
Probabilistic models define a probability distribution over features and labels.
Okay, so when we provide yellow, curved, no leaf, and 6 O's and banana as the prediction, it will tell us the probability of these features being banana is 0.004. However, if we were using a classifier, it will tell us that it is banana or not. Okay. So here we predict the probability of it is being banana, and here we the classifier directly put it into a site and tell us that it is banana or not. There is no probability.
Probabilistic models, classification. Probabilistic models define a probability distribution over features and labels. Given an unlabeled example, yellow, curved, no leaf, 6 ounces predict the label. How do we use a probabilistic model for classification, prediction?
Okay, so we get the probability of both banana and apple. So it says it is 0.004 probability that banana, and it is 0.00002 probability apple. Therefore, it has higher probability for banana. Therefore, we can count it as banana. Okay.
For each label, ask for the probability under the model. Pick the label with the highest probability.
So we can use probabilistic model as a classifier with this approach. We get the probability of input for each class that we have, and then we can count it, or we can assume it that the highest probability is the correct label. Okay. So probabilistic model versus classifier. The classifier tells us a single probability. It says that it is 100% banana. However, the probabilistic models tells us that it is this much percent a particular label, and another percent a particular label. So why probabilistic models we should use over classifiers?
Probabilities are nice to work with. Range between 0 and 1 can combine them in a well-understood way. Lots of mathematical background, theory and aside, to get the benefit of probabilistic output. You can sometimes calibrate the confidence output of a non-probabilistic classifier. Provide a strong, well-founded groundwork. Allow us to make clear decisions about things like regularization. Tend to be much less heuristic than the models we've seen. Different models have very clear meaning.
So you see, we are able to evaluate our model performance with this. We can see that it tells, let's see, it is 200 times more likely to be banana than apple. You see, I am able to evaluate the difference here. However, in here, I am not able to evaluate the difference. If it is one time, maybe this classifier can be very slightly picking the side of banana, but I won't know it. However, when we use a probabilistic model, I will be able to tell that this is 200 times more likely to be banana than apple. You see the difference? This is much more clear and easy to evaluate and understand. Okay, so this is the benefit of probabilistic model. Okay, I will take a pause. Okay.
Probabilistic models, big questions. Which model do we use, i.e., how do we calculate P feature label? How do train the model, i.e., how do we estimate the probabilities for the model? How do we deal with overfitting? Same problems we've been dealing with so far. Probabilistic models. Which model do we use, i.e., how do we calculate P feature label? ML in general. Which model do we use? Decision tree, linear model, non-parametric. How do train the model, i.e., how do we estimate the probabilities for the model? How do train the model? How do we deal with overfitting? How do we deal with overfitting?
So you see, the questions of probabilistic models are almost same as the questions in general machine learning.
Basic steps for probabilistic modeling. Step 1. Pick a model.
Okay.
Step 2. Figure out how to estimate the probabilities for the model. Step 3. Optional. Deal with overfitting.
Okay, so step 1. Okay, in the step 1, before starting with the model,
What was the data generating distribution?
so we have training data, test data from our data generation distribution. Okay, and so this was a reminder of how it was.
Step 1. Picking a model. What we're really trying to do is model is the data generating distribution, that is how likely the feature label combinations are.
Okay, then there is some maths. What rule we are going to take? You see. Okay.
So far we have made no assumptions about the data. How many entries would the probability distribution table have if we tried to represent all possible values, e.g. for the wine data set?
Okay, how many possible values we would have? So let's consider it as like this.
Full distribution tables.
Okay, so the chicken problem.
All possible combination of features. Approximately 7,000 binary features. Sample space size, 27,000 equals?
So the sample space size can be 2 power 7,000. You see how much this would make? This is impossible to calculate all of the combinations of features. Okay, it is impossible. So it is something like this. You see, there is no way to store this amount of data anywhere in the earth, probably.
Storing a table of that size is impossible. How are we supposed to learn, estimate each entry in the table?
Okay, so far we have made no assumptions.
Model selection involves making assumptions about the data. We did this before, e.g. assume the data is linearly separable. These assumptions allow us to represent the data more compactly and to estimate the parameters of the model. An aside, independence. Two variables are independent if one has nothing whatever to do with the other. For two independent variables, knowing the value of one does not change the probability distribution of the other variable or the probability of any individual event. The result of the toss of a coin is independent of a roll of a dice. Price of tea in England is independent of the whether or not you pass AI. Independent or dependent. Catching a cold and having cat allergy. Miles per gallon and driving habits.
Okay, so this is dependent, as you can see. So depending your driving habits, how many miles you can go with per gallon changes. Catching a cold and having cat allergy has nothing in dependency. Height and longevity of life, these also have some kind of dependence, I think we can say. If you are too tall, it may affect your longevity of life, but I'm not sure we can count this as dependent of or not. We need more statistical analysis probably.
Independent variables. How does independence affect our probability equation's properties? If A and B are independent, written.
So if A and B are independent, what is the probability of A and B? What is the probability of A when B happens? What is the probability of B when A happens? Okay, so let's see them. If A and B are independent, the probability A and B is equal to PA multiplying with PB the probability of PA is PA, the probability of PB is PB. So this is about independence. However, if they were okay, still we are continuing with independent variables. So if they are independent,
reduces the storage requirement for the distributions, reduces the complexity of the distribution, reduces the number of probabilities we need to estimate.
okay, so if they are
Conditional independence. Dependent events can become independent given certain other events. Examples: height and length of life, correlation studies, size of your lawn and length of life. If A, B are conditionally independent of C,
it is like this, like this, like this, but PA and B does not equal to PA multiplying PB. Why? Because A and B are independent of C, not they are independent themselves. Okay, so this is the key issue here.
naive Bayes assumption.
Okay,
What does this assume? Assumes feature I is independent of the other features given the label.
okay.
Assumes the probability of a word occurring in a review is independent of the other words given the label. For example, the probability of fish occurring is independent of whether or not meat occurs given that the review is about chicken.
Is this true? I think not. Okay, so let's come to the realities.
For most applications, this is not true. For example, the fact that chicken occurs will probably make it more likely that meat occurs. However, this is often a reasonable approximation.
So there is something called as naive Bayes assumption. When we search for it, I think we can see it inside Wikipedia.
In statistics, naive Bayes classifiers are a family of simple, probabilistic classifiers based on applying Bayes' theorem with strong, naive independence assumptions between the features. They are among the simplest Bayesian network models, but coupled with kernel density estimation, they can achieve higher accuracy levels.
So you see, it assumes that there is a strong independence. Okay.
Naive Bayes classifiers are highly scalable, requiring a number of parameters linear in the number of variables, features, predictors in a learning problem. Maximum likelihood training can be done by evaluating a closed-form expression, 718, which takes linear time, rather than by expensive iterative approximation as used for many other types of classifiers. In the statistics and computer science literature, naive Bayes models are known under a variety of names, including simple Bayes and independence Bayes. All these names reference the use of Bayes' theorem in the classifier's decision rule, but naive Bayes is not necessarily a Bayesian method.
Okay.
P, y is the probability of a particular feature value given the label. How do we model this? For binary features, for discrete features, i.e. counts, for real valued features.
Okay, the feature can be binary, 0 or 1. It can be discrete features such as 1, 2, 3, 4, 5, 6, or it can be real valued features such as 1.5 or 2.3 and such. So for binary features such as coin toss, if it is equal to x1, this or this, let's see it from the slide, PowerPoint slide. Okay, so it is like this. Let me remove this node area. Okay. So you see, it is the first condition if x equal 1 or otherwise. It is so simple, it is binary.
Other features. Could use lookup table for each value, but doesn't generalize well. Better, model as a distribution. Gaussian, i.e. normal, distribution, Poisson distribution, multinomial distribution, more on this later. Basic steps for probabilistic modeling.
Okay, so the step 2.
Step 2, figure out how to estimate the probabilities for the model. Obtaining probabilities. We've talked a lot about probabilities, but not where they come from. How do we calculate P, Xi, Y from training data? What is the probability of surviving the Titanic? What is that any review is about Pinot Noir? What is the probability that a particular review is about Pinot Noir?
And obtaining probabilities. So we use math and estimating probabilities.
What is the probability of a chicken meat review? We don't know. We can estimate that based on data, though. Number of review labeled chicken meat.
Dividing with number of total reviews. So this is called the
This is called the maximum likelihood estimation. Why? Maximum likelihood estimation, MLE. Maximum likelihood estimation picks the values for the model parameters that maximize the likelihood of the training data. You flip a coin 100 times. 60 times you get heads. What is the MLE for heads?
It is 0.60, of course. So there are some videos that you can watch to learn about distributions. The normal distribution, the maximum likelihood. Here the normal
StatQuest makes me crazy when it's upside.
Okay, so here the normal distribution, like this. You can watch this video, and then there is maximum likelihood distribution.
StatQuest.
This guy explains this extremely well. Okay, and then probability versus likelihood and likelihood for the normal distribution step by step. So I want you to watch these videos and then continue to the slide or my video.
Maximum likelihood estimation picks the values for the model parameters that maximize the likelihood of the training data.
Okay.
You flip a coin 100 times. 60 times you get heads. What is the likelihood of the data under this model? Each coin flip is a data point. MLE for heads, P, head equals 0.60.
Okay, so this is the maximum likelihood, and
what is the likelihood of the data under this model? Each coin flip is a data point.
it is calculated like this.
Log 0.6060 asterisk 0.4040 equals minus 67.3.
Let's see if this is true. Yeah, okay.
Can we do any better? P, heads equals 0.5 log 0.5060 asterisk 0.5040 equals minus 69.3.
Okay, so this is the probability of head and this is the probability of tail. And when we do 100 times flips, the probability of it is being like this is not like this, as you can see. And the p heads, if we count p hats as the probability of hat is 0.7, it is resulting like this. Okay, so then there are some articles, like let's see them.
Probability concepts explained, maximum likelihood estimation. Introduction. In this post I'll explain what the maximum likelihood method for parameter estimation is and go through a simple example to demonstrate the method. Some of the content requires knowledge of fundamental probability concepts such as the definition of joint probability and independence of events. I've written a blog post with these prerequisites, so feel free to read this if you think you need a refresher.
Okay, we know them already. We have seen them in the first chapter. Okay, so let's continue. What are parameters? Okay.
Often in machine learning we use a model to describe the process that results in the data that are observed. For example, we may use a random forest model to classify whether customers may cancel a subscription from a service, known as churn modeling, or we may use a linear model to predict the revenue that will be generated for a company depending on how much they may spend on advertising. This would be an example of linear regression. Each model contains its own set of parameters that ultimately defines what the model looks like. For a linear model we can write this as y equals mx plus c. In this example x could represent the advertising spend and y might be the revenue generated. M and c are parameters for this model. Different values for these parameters will give different lines. See figure below.
Okay, so this is the linear model, and let's continue.
So parameters define a blueprint for the model. It is only when specific values are chosen for the parameters that we get an instantiation for the model that describes a given phenomenon. Intuitive explanation of maximum likelihood estimation. Maximum likelihood estimation is a method that determines values for the parameters of a model. The parameter values are found such that they maximize the likelihood that the process described by the model produced the data that were actually observed. The above definition may still sound a little cryptic, so let's go through an example to help understand this. Let's suppose we have observed 10 data points from some process. For example, each data point could represent the length of time in seconds that it takes a student to answer a specific exam question. These 10 data points are shown in the figure below.
Okay.
We first have to decide which model we think best describes the process of generating the data. This part is very important. At the very least, we should have a good idea about which model to use. This usually comes from having some domain expertise, but we won't discuss this here. For these data we'll assume that the data generation process can be adequately described by a Gaussian normal distribution. Visual inspection of the figure above suggests that a Gaussian distribution is plausible because most of the 10 points are clustered in the middle with few points scattered to the left and the right. Making this sort of decision on the fly with only 10 data points is ill-advised, but given that I generated these data points we'll go with it. Recall that the Gaussian distribution has two parameters. The mean, mu, and the standard deviation, sigma. Different values of these parameters result in different curves, just like with the straight lines above. We want to know which curve was most likely responsible for creating the data points that we observed? See figure below. Maximum likelihood estimation is a method that will find the values of mu and sigma that result in the curve that best fits the data.
Okay, from this, I would say F2 is the most likely one. Let's see.
The 10 data points and possible Gaussian distributions from which the data were drawn. F1 is normally distributed with mean 10 and variance 2.25. Variance is equal to the square of the standard deviation. This is also denoted F1n, 10, 2.25. F2n, 10, 9, F3n, 10, 0.25, and F4n, 8, 2.25. The goal of maximum likelihood is to find the parameter values that give the distribution that maximize the probability of observing the data.
Okay, so this is the key point.
The goal of maximum likelihood is to find the parameter values that give the distribution that maximize the probability of observing the data. The true distribution from which the data were generated was F1 tilde n, 10, 2.25, which is the blue curve in the figure above.
Okay, so it was F1, not F2.
Calculating the maximum likelihood estimates. Now that we have an intuitive understanding of what maximum likelihood estimation is, we can move on to learning how to calculate the parameter values. The values that we find are called the maximum likelihood estimates, MLE. Again, we'll demonstrate this with an example. Suppose we have 3 data points this time and we assume that they have been generated from a process that is adequately described by a Gaussian distribution. These points are 9, 9.5.
Okay, sorry about the interruption.
Again, we'll demonstrate this with an example. Suppose we have 3 data points this time and we assume that they have been generated from a process that is adequately described by a Gaussian distribution. These points are 9, 9.5 and 11. How do we calculate the maximum likelihood estimates of the parameter values of the Gaussian distribution mu and sigma? What we want to calculate is the total probability of observing all of the data, i.e. the joint probability distribution of all observed data points. To do this, we would need to calculate some conditional probabilities, which can get very difficult. So it is here that we'll make our first assumption. The assumption is that each data point is generated independently of the others. This assumption makes the maths much easier. If the events, i.e. the process that generates the data, are independent, then the total probability of observing all of data is the product of observing each data point individually, i.e. the product of the marginal probabilities. The probability density of observing a single data point x, that is generated from a Gaussian distribution, is given by the semicolon used in the notation p, x, mu, sigma is there to emphasize that the symbols that appear after it are parameters of the probability distribution. So it shouldn't be confused with a conditional probability, which is typically represented with a vertical line, e.g. p, a, b. In our example, the total joint probability density of observing the 3 data points is given by.
Okay, it is calculated like this, as you can see.
We just have to figure out the values of mu and sigma that results in giving the maximum value of the above expression. If you've covered calculus in your maths classes, then you'll probably be aware that there is a technique that can help us find maxima and minima of functions. It's called differentiation. All we have to do is find the derivative of the function, set the derivative function to 0 and then rearrange the equation to make the parameter of interest the subject of the equation. And voila, we'll have our MLE values for our parameters. I'll go through these steps now, but I'll assume that the reader knows how to perform differentiation on common functions. If you would like a more detailed explanation, then just let me know in the comments. The log likelihood. The above expression for the total probability is actually quite a pain to differentiate, so it is almost always simplified by taking the natural logarithm of the expression. This is absolutely fine because the natural logarithm is a monotonically increasing function. This means that if the value on the x-axis increases, the value on the y-axis also increases, see figure below. This is important because it ensures that the maximum value of the log of the probability occurs at the same point as the original probability function. Therefore we can work with the simpler log likelihood instead of the original likelihood. Taking logs of the original expression gives us. This expression can be simplified again using the laws of logarithms to obtain. This expression can be differentiated to find the maximum. In this example we'll find the MLE of the mean, mu. To do this we take the partial derivative of the function with respect to mu, giving. Finally, setting the left-hand side of the equation to 0 and then rearranging for mu gives. And there we have our maximum likelihood estimate for mu. We can do the same thing with sigma too, but I'll leave that as an exercise for the keen reader.
Okay, so you see this is how we calculate the maximum likelihood parameters. And let's see the conclusion remarks.
Concluding remarks. Can maximum likelihood estimation always be solved in an exact manner? No is the short answer. It's more likely that in a real-world scenario the derivative of the log likelihood function is still analytically intractable, i.e. it's way too hard, impossible to differentiate the function by hand. Therefore, iterative methods like expectation maximization algorithms are used to find numerical solutions for the parameter estimates. The overall idea is still the same though. So why maximum likelihood and not maximum probability? Well, this is just statisticians being pedantic, but for good reason. Most people tend to use probability and likelihood interchangeably, but statisticians and probability theorists distinguish between the two. The reason for the confusion is best highlighted by looking at the equation. These expressions are equal. So what does this mean? Let's first define p data, mu, sigma. It means the probability density of observing the data with model parameters mu and sigma. It's worth noting that we can generalize this to any number of parameters and any distribution. On the other hand, L, mu, sigma, data, means the likelihood of the parameters mu and sigma taking certain values given that we've observed a bunch of data. The equation above says that the probability density of the data given the parameters is equal to the likelihood of the parameters given the data. But despite these two things being equal, the likelihood and the probability density are fundamentally asking different questions. One is asking about the data and the other is asking about the parameter values. This is why the method is called maximum likelihood and not maximum probability. When is least squares minimization the same as maximum likelihood estimation? Least squares minimization is another common method for estimating parameter values for a model in machine learning. It turns out that when the model is assumed to be Gaussian as in the examples above, the MLE estimates are equivalent to the least squares method. For a more in-depth mathematical derivation, check out these slides. Intuitively we can interpret the connection between the two methods by understanding their objectives. For least squares parameter estimation we want to find the line that minimizes the total squared distance between the data points and the regression line, see the figure below. In maximum likelihood estimation we want to maximize the total probability of the data. When a Gaussian distribution is assumed, the maximum probability is found when the data points get closer to the mean value. Since the Gaussian distribution is symmetric, this is equivalent to minimizing the distance between the data points and the mean value.
Okay, and there is another article. Okay, I will leave it to you. And there is another video. Okay, then we have probabilistic models. Okay, 1 second. Okay, let's continue.
Maximum likelihood estimation (MLE). You flip a coin 100 times. 60 times you get heads and 40 times you get tails. What is the probability for heads?
It is this y likelihood. Okay, we have seen it. Okay, let's analyze it.
The likelihood of a data set is the probability that a particular model, i.e. a model and estimated probabilities, assigns to the data.
Likelihood data, it is like this. For each example I to the n, the model parameters, e.g. probability of heads, how probable it is under the model. Okay, so this is the probable, this is the probability of heads, likelihood. Okay, so
What is the likelihood of this data with theta equals p, head equals 0.6?
so the likelihood is calculated like this, and it is extremely unlikely, probably. Let's see. Okay, so
The maximum likelihood estimate for a model parameter is the one that maximizes the likelihood of the training data. Given some training data, how do we calculate the MLE? You flip a coin 100 times. 60 times you get heads and 40 times you get tails.
okay, so it is calculated like this. You see 60 multiplying with log p heads, probability of heads, plus 40 with log p tails, probability of tails. So it is like this. And MLA is the maximum of this. So when we calculate it, we get this point. Okay. Okay, p head, so it is getting negative 67.3. Can we do any better? If the probability of heads were 0.7 instead of 0.5, we would get this probability. So our estimates are, let's see. Okay, we have seen this. Okay. Okay, some math. Okay.
Maximum likelihood estimation. Intuitive sets the probabilities so as to maximize the probability of the training data. Problems: overfitting. Amount of data particularly problematic for rare events is our training data representative.
And finally, deal with overfitting. Okay, so okay, not parasitic is 1 over 100,000. You see, this data is extremely unbalanced in this example. So what can we do? So it is being non-parasitic is equal to something like this. So probability of us finding one is equal to about 10%, in which case we would incorrectly assume the probability is 1 over 10,000. It is 10,000 too large. So the solutions, let's see. So our data has to represent our case as well. So if you flip coin 4 times only, you get the probability of 75% heads, which is extremely incorrect. If you flip it 40 times, you still may get 75%. If you flip 2 times and get 2 tails, you see you get 0. However, if you flip it 1000 times and if you get 497 heads and 503 tails, you get almost 50%, which is the real probability. This is about probabilistic methods. I think there should be some Python libraries probably. Okay, so let's see if do they have any framework. Okay, probably this is about something has written Python for maximum likelihood estimation. Okay. Okay, if you happen to use probabilistic algorithm, let's see. Okay, so project description, production. So probabilistic data structures and algorithms in Python. What are the algorithms? Okay, you see it is also hard to find a good library for probabilistic machine learning. Let's search for C# if there is any probabilistic. Okay, so they support probabilistic learning, which uses, let's see. Oh, they just use kernel for probabilistic. I see.
Instead of producing probabilistic outputs, support vector machines express their decisions in the form of a distance from support vectors in feature space. In order to convert the SVM outputs into probabilities, Platt 1999 proposed the calibration of the SVM outputs using a sigmoid logit link function. Later, Lin et al. 2007 provided a corrected and improved version of Platt's probabilistic outputs. This class implements the later. This class is not an actual learning algorithm, but a calibrator. Machines passed as input to this algorithm should already have been trained by a proper learning algorithm such as sequential minimal optimization (SMO).
Okay, so this shows, the following example shows how to calibrate SVM that has been trained to perform a simple XOR function. So it uses sequential minimal optimization with Gaussian distribution. So the kernel is like this and complexity is like this. It learns, and when we do prediction, it should be outputting the probabilities probably. Okay, you can test it if you want, or you can find other algorithms. Okay, I think this is enough for this week. I will upload to the YouTube. You get the idea of probabilistic models. This is it is what is important. If your task is about probabilities or fit better for probabilistic methods, you should use them. If not, you can use other methodologies. End of lecture. Hopefully see you next week.